Assalamualaikum warahmatullahi wabarakatuh. We meet again. So this is the uh, subtopic under rectifiers on the rectifier chapter. So this is what we call half wave rectifier using control power device, which is SCR. So this is the circuit where, as you can see, uh, this is a circuit of the control rectifier connected with our load. Okay, and as you may recall that this SCR or thyristor can only be turned on when both conditions are met. So what are the both conditions? So this is the condition. The first one, the SCR must be forward biased, meaning that the anode must be positive compared to the cathode. And the second condition, the current must be supplied to the gate of the SCR to trigger it on. Okay, so the triggering signal is actually just a very small short period of time. It's not okay, so as for example like this, so this is the triggering signal for the SCR, a very short triggering signal. For example, if you are, so as you can see here, um, very simple circuit. Okay, so as you can see, we have a voltage source, okay, signal here, voltage waveform here, and even though the SCR is forward bias, okay, but there is no triggering signal, so the V out will remain zero because the SCR is off. Okay, so V out is remain zero, but at angle of alpha, okay, time of alpha here, or sometimes also we call angle. Okay, we call alpha is actually a firing angle. Okay, this alpha is actually referred as a firing angle. So when it is triggered, okay, so the SCR is forward biased already and triggered, so the SCR will turn on and V out is connected with the V source. Okay, so the V out waveform is will actually similar or equal to the voltage source, like this. Okay, and when the source is going for the negative cycle, okay, the SCR will actually in forward bias, sorry, will be in a block, will be in a reverse blocking. Okay, so meaning that the SCR will turn off, and turn off meaning that the load is no longer connected with the input. So that's why we have a zero V out during the negative cycle. Okay, and then when it is positive cycle back, okay, and there is a triggering signal, so it will actually have an output again. So this is the equations to calculate the V out average and V out RMS. Okay, so the derivation is similar to what we have done in the previous R load with diode. Okay, but after the derivation, we will come out with the V out average should be in this form: Vm over 2 pi plus multiply with 1 plus cos alpha. Okay, and alpha is actually a firing angle, or sometimes also we call delay angle. And if you note that if the firing angle is zero, meaning that there is no delay, the firing angle is zero, so there is no delay. So when we substitute the alpha here, okay, so this one will become cos alpha is equal to 1, so meaning that we have Vm over 2 pi. This one will become 1 plus 1, which is Vm over pi finally. So you may recall this Vm over pi is similar to the half-wave rectifier using diode. Okay, using diode, because diode is actually when you forward bias, so it will automatically turn on. Okay, so seems like the SCR here, if the alpha is no long, if there is no delay angle or the firing angle. Okay, so since this is the R load, so the I out average can be simply use this formula, V out average over R. And this is for the RMS voltage, so this is the equation. Okay, so mean that since this is R load only, so this one, the I out RMS can be simply by using V out RMS over R. So this is the example 3. Source is a sinusoidal 240 volt RMS at frequency 50 Hertz. The load is 150. So it's been given 150 ohm load. So this one is 240 volt RMS. Delay angle given is actually 30 degrees. So this is your alpha. So determine the average of voltage, average load current, and power absorbed by the load. So this one I would like to use the whiteboard here. So as you can see here, this is the equations. So the first one will be a very what I call straightforward solution, the average output voltage. So you can use this formula. Okay, then use this formula to obtain your V out average. So your V average is 240 volt. You need to multiply with square root 2 over 2 pi 1 plus cos 30 degrees. Okay, so by using calculator, you can obtain the value of 100.8 volts. And so this is for A. And then the second question is the average load current, so which is I average. So you just use B out average over the load, which is 150 ohm, right? So this one 100.8 over 150 ohm. So you will get 0.67 ampere. And lastly, the average power absorbed by the load. Okay, so P out average is actually, you need to use V out RMS equations. Okay, V out RMS equation, or you can use, I think because we have already the I out RMS. Okay, so you need to use this formula. Okay, multiply with R. Or also you can get V out RMS square over R load. Okay, so I'm using this third equation here. I will use this because it's much easier. So we go for V out RMS, which is Vm over 2 square 1 minus, I think minus, I also don't remember, alpha over pi plus sine 2 alpha over 2 pi. Okay, please check. So I think that's okay. Okay, so as you can see here, this is the I out RMS equations. Okay, and you need to convert Vm. It's actually 240 volt. You need to multiply with the square root 2. And for this alpha is 30 degrees, but the pi here is actually in radian. So you need to convert the value into a radian. So it's very simple. So just 30 degrees over your 180 degrees multiplied with pi. Okay, or you can use 30 over 360 degrees multiplied with 2 pi. So either both can be is actually correct answer. Okay, so by using this, I have the value of the alpha is 0.52. okay, and sine to alpha, so 60 degrees. So the answer should be by using your calculator. So I got by using calculator, so just simplifying, so I got this one is 0.97, so uh, 0.97 square, so multiply with 240 volt, multiply with square, sorry, square root 2 over 2. So I will have my is actually 167 volt. Okay, so and then my P out average, which is your P active actually, so 160 volts square over your R. Okay, so this one 160 volt over R is 150 ohm, so I will get around 186.24 watt. Okay, so every time if you have been uh, asked about how to obtain the P out average, so meaning that you need to use the RMS value instead of average voltage and average current. So we have completed our example 3. So we move to the example 4. So this is actually a design questions. So even though it is a design question, so it is a still straightforward. So let's discuss the solution for this one. So this is example 4 design solution. So it been given V in equal to 240 volt RMS, and unit and the V average is given 100 volt and the load resistance is 80 ohm. So the answer, the question is actually to ask you to find what is the suitable alpha for this to get this average output voltage for about 100 volt. So by using the equation here, so it's very simple. You just need to substitute all the values so you can obtain the alpha. So by using calculator, so I have simplified. So I finally obtained these values. So 0.589 equal to 1 plus cos alpha. Okay, so we maybe we arrange this. So this one cos alpha will become negative. Okay, so this one is actually 0.589 negative 1. So it will give you negative 0.4, okay, negative 0.41. So alpha is inverse of course negative 0.41. So this one will give you the value of 114 degrees, 0.25. So that is the answer. The second question is to find the average load current. So since this is R load, so the I out average can be simply by using this, can be obtained by using this, this equation, V out over R. Okay, so V out average, as you all know, so we have 240 volts square root 2 over 2 multiplied with 1 cos alpha is 114.25, okay, over your R load, which is your R is 80 ohm, if not mistaken. I think yes, 80 ohm. Okay, and then you can get this one is actually 1 minus Okay, so my answer is 1.25 ampere. So we have completed the example 4. Next is the single phase control using thyristor half wave. But right now it is connected with inductive load or RL load. Okay, and this is the voltage source in waveform, and the second graph here shows the output of the voltage and also the current. And as you notice, the current is no longer linear, okay, because you have this inductor element here, okay, because we have the inductor. So the inductor will actually act as an energy storage in this load. Okay, so that's why the current is no longer linear, because it will charge and discharge. So actually the principle is the same with the diode RL, with the RL load. The only difference is actually we have what we call the delay angle here at the output. Okay, so when the input voltage is a positive cycle, so the SCR will forward bias, but still the triggering signal is not given, so it will remain off and V out is equal to 0. And when a triggering signal is given, okay, at the application of alpha here, a very small short period of time, so the SCR will turn on and the current will flow, okay, the current will flow, okay, and actually charging this inductor, okay. And the voltage, as you can see, is following the shape of the voltage input. Okay, at this point where the voltage source is going to the negative part of its cycle, and as you can see, okay, this SCR will force to remain on because the inductor, the energy stored in this inductor need to be discharged, okay, need to be discharged, and it will force the SCR to turn on. So right now the V out is still connected to the VS, so that's why we have the waveform of the V out is still following the voltage waveform of the Vs until at the position of beta, where suddenly the V out is 0. This is happen when the energy inside the inductor is already discharged, totally discharged. Okay, and as you can see here, the current of the inductor, so it will increase slowly charging, and at this point it will start to uh, discharge until the energy is become 0. Okay, why become become 0? So when the energy becomes 0, so there is no force to turn on this SCR. So since the SCR is in the reverse bias, so it is turned off, okay, and the V out is disconnected from the V source, and that's why we have output voltage is equal to 0 until to the next cycle of the positive cycle of the source. Okay, so I hope you understand the operation of the RL load with the SCR. So actually, this is actually how we derive the current, which is the nonlinear equation of the current. We have, as you can see, we have two parts you need to actually derive. We have the current due to the pulse response, okay, and the current that due to the no response. And then you have this equation, okay, and then this A here is a constant, And to obtain this A value, so please we set the initial value like this. So we substitute omega t equal to alpha and set the output is 0. So finally we will have the A value as this equation. Okay, and finally, for summarize for the inductor current, so this is the equation for the nonlinear inductor, the nonlinear current here, and this is only appear from alpha to beta. So as you can see here, the current only will flow from alpha to beta, and otherwise the current is remain 0. Okay, and the extinction angle is actually where the current is actually becomes 0, or the energy becomes 0. So this is the equation, but normally it is cannot be solved cannot be solved in manual calculation. It can only be solved by using numerical methods. And this is the average value equations for the RL load using the thyristor. Okay, and since this is the value and this is the average current, so you need to actually integrate the current here, which is very complicated because the current is no longer linear, it's no longer sinusoidal, it's a non-linear current. The RMS current also, so you need to integrate this one, and the power absorbed by the load is actually you need to use this I RMS square multiplied with R. Okay, for this load you cannot use this formula. Okay, so if you are using this formula for the load, so this is totally wrong, because because as you can see, the load right now consisted of two elements. This is B out, while we only want the P only absorbed by R. Okay, so meaning that if you want to use this, you need to use to calculate V that across the resistor. Then this is correct. Okay, if you are using V out over R, so this one is incorrect. Okay, that's why for in engineering, we are prefer to use this one. Okay, so example 5, I think we will try to solve this during our online class. And this is the half-wave rectifier with RL source load. Okay, so even though this topic is quite large, but we will go briefly. Okay, so this is, you have the AC source and you have DC source, and this we consider as our V out here. So in this circuit, okay, the diode will remain off as long as the voltage of the AC is less than DC voltage. Okay, and as you can see here, the intersection here, the current only flow after when the VAC is higher than the V source, higher than the VDC. Okay, because this is, as you can see, by using the KVL here, this diode is only forward bias when VAC, when the anode is positive compared to the cathode. Okay, which is currently supplied by the VDC. Okay, and the alpha is actually the angle where the current start to conduct. So this one can be simply calculated by using this equation. So where this is the point where the VAC and VDC is intersect. So based on this, we can use this equation and we can have the value of the alpha as this one. Okay, and then this is the current value derivation and so on. Okay, and I think this one shows the V out equation. I think this one is not scale out. It's not very it's not following the scale. So I think this one, I think I plot with the red value here, red line here. So this is the V out, following the V out, V input, and then like this, and then straight using VDC. Okay, and then again. Okay, so that is actually the waveform of the output voltage. Okay. And this is the average output DC current and the RMS current, and this is actually the power equation related, and this is for the RS source load control. Actually similar with the diode, but it's actually have an what I call the alpha. Okay, and as you can see here, the difference is that we have what I call the firing angle delay here. So since even though the SCR is fault biased, but if there is no triggering signal, so it will remain off, okay, until the triggering signal is given. Okay, that's all.